Tonight. This was a collaboration with Hamptons Observatory, and I want to turn it over now to Donna McCormick, who's the Executive Director of the Hamptons Observatory, who's responsible for this event tonight. Please welcome Donna McCormick.
Thank you, Ben, and thank all the kind folks at Rogers Memorial Library for co-hosting this. I am with Hamptons Observatory, and how many people have heard about that before? I know Julia has. Really? Okay, we were started in 2005 for the purpose of fostering interest in science and astronomy in particular. And it seems like almost since then we've been trying to actually get an observatory established and functioning. Right now we are based in East Hampton on the campus of the Ross School. We have a 20-inch mega research telescope, but the building itself is having some functional issues. So we're hoping sometime in the not too distant future to invite you all out there and take a look at the telescope. We do have star parties as we do lectures throughout the Hamptons. And we also have a lot of virtual lectures, which if you can attend at the time, we do post them on YouTube afterwards. I've got a list here, if you haven't received it, of upcoming events. I've got in July 17th, there's a virtual lecture on the Apollo-Soyuz mission by Andy Paneros, who's a NASA Solar System Ambassador. This is a virtual lecture, and he's actually going to describe all of the Apollo missions, as well as discuss his experiences with astronauts. He's a science reporter and a radio show host, so he's been quite a few of them, so have some interesting personal anecdotes. And then on August 19th at the East Hampton Library, we're going to have the former longest-running chairman of the astronomy department at Columbia University, David Elfins. He's going to be doing a book signing on his current book called Universal Timekeepers, Reconstructing History Atom by Atom. And we have some other events coming up, which I just haven't quite finished setting the dates for. But anyway, I'd like to introduce our speaker, Jonathan Schachter, who received his PhD in physics from UC Berkeley in 1990. He was a postdoc at the Harvard Smithsonian Center for Astrophysics from 1990 to 2000, where he also co-founded a collegial Friday get-together known as the Movable Feast, which exists to this day, and which he often attends by Zoom or in person in Cambridge. In 1996, Jonathan joined Chandra as the scientific lead for software testing and attended the 1999 launch. In 2000, he switched careers and went to Wall Street. He has focused on the testing and validation of mathematical models since the great financial crisis. He is the lead author of a model risk textbook that will appear in bookstores in January. He resides both in Southampton and in Blackish. So if you would join me in welcoming Jonathan Schachter.
Thank you, Donna. And before I start, I definitely second David Elfin. I know him very well. Quite a character. I believe when he was at Columbia, he refused tenure and wanted to work out on a contract because he did not like the idea of tenure. Also had a long ponytail, so Columbia's got a great department, and Elfin fit right into it in terms of personality, but also the high level of the science. So today I'd like to talk to you about an observatory in space, the Chandra X-ray Observatory. My title now is I'm the CEO of a financial engineering company, and I was part of the software test team from 1996 to about a month or two after launch when all the systems were checked out. So, but a little bit more about me. So I was born near the Little Red Lighthouse and the George Washington Bridge in Washington Heights. And I really liked meteorology. I'd been scientific and a great kid where you could measure snowfall and wind speed. Like it was that kind of stuff at age 8 or so. Loved the Hayden Planetarium, which is another fantastic. Elfin and I, we all know Neil deGrasse Tyson, who's been a great popularizer of astronomy, and spent some time at Columbia. When I was younger, I vacationed on Shelter Island with my family, and I still like corgis. And I think I probably first saw the Perseid meteors coming up in August in the dark luminous sky. So a lot of people don't know this, but I put out these winter sowing containers in the cold winter, January, February. I put seeds and dirt in them, and they're homeostatic mini greenhouses. And I still have 6 of them left. That was when we were fully at 40. So basically, you get your own little seedlings popping up, which is very cool. Anyway, I like that. So edibles and flowers, and it's a lot of fun. Creation. All right, so basically what I'd like to do is give you a little bit more about my background. Oh, this is animated, it's moving. Okay, I gotta stop touching it. Anyway, a little bit about X-ray astrophysics because that leads well into Chandra. I'll talk about Chandra himself, that's a person, and then the satellite. Right, there you go, the scientist and the satellite. And then I'll give you, after showing you some an animation and some actual Chandra data, I'll throw it open if we have time to take requests, and we can hit the Chandra site, and you can pick a year, a celestial body type, and go to town. A lot of very interesting sources, former colleagues of mine who maintain the Chandra archive at Harvard. That's the images on demand that's taken by me. So, a little bit about me. So I want to try to make this a continuous life of studying atoms and ions. So I studied first in Princeton atomic physics, 2 elements, rubidium and xenon. Rubidium is in the first group, so it's like sodium, potassium, and lithium. With 1 valence electron, and xenon is a lone gas. You can actually get them to interchange the quantum mechanical spin. So it's an interaction between atoms. It's independent research. I then, I'll talk about it a little bit more, but I studied the atoms oxygen and helium interacting with each other, the phenomenon called Poland fluorescence. And why that's interesting is because while you can't see things around black holes, you can, from atomic physics, infer how far they are away and how large they are. That's valuable information. You usually can't see unless something is a planet or very nearby. Microphones? Okay. So, yeah. Right, and then basically I think you have the rest of the dates. 96 I was the scientific lead, and after the testing was completed, maybe some people will get this joke, but I went from black holes to black shoals. Just to tell you a little bit about what a rocket scientist on Wall Street does, as Donna said, since the great financial crisis, some of us believe that a single model was the cause of the great financial crisis. And the Fed put out guidance after that saying we have to, that, you know, when, that basically too many people were using the same model, just like you wouldn't just invest in one asset. The Gaussian Coppola model especially for bespoke CEOs. So since 2011, basically, it's been a whole industry trying to figure out whether mathematical models are sound and whether they're maintained. Something like maintaining a car or a house. I am a long-time Southampton resident. We bought our home in 1985. It was the peak of mortgage rates. I think we got like a 10 or 11% mortgage in 85. Refinanced it within a year or two. And that's right. I'm the lead author of the forthcoming textbook that's for master's level students in financial engineering and teaches them how to test mathematical models more than just kick the tires, but really make them and test them independently of the people who don't, which is a lot of testing goes into satellites as well. That's the reference. Okay, so what is X-ray astrophysics? It may not be something you think of today. So first, let's say that everything from the smallest scale, even the Earth, to clusters of galaxies can emit X-rays. indeed stars at their young age, stars being born, stars in middle age, the so-called main sequence, and even elderly stars can all participate in this. And the physics then is extreme, like 1 million degrees. That's pretty hot, even compared to today. Very high pressure. In fact, the pressure limits are often defined by gravity trying to collapse something, and something like relativity or quantum mechanics keeping it from collapsing. So it's very, very dense. I also talked a little bit about atomic physics, so let me talk a little bit more about what happens in astronomy. First of all, it's very common for neutral atoms to be the things that we consume. But they're multiply ionized. Basically, the temperature and pressure is so extreme that you can strip all the electrons off an atom. Well, that's easy to model. Most commonly, though, you may just have one electron on the atom, and it turns out, if you studied some physics, that's a very simple problem to solve. It's basically just hydrogen, and hydrogen's the simplest atom that there is. You just have to have that there's a much heavier nucleus. So, but basically what you see is you see different spectral lines, and that tells you that there are things like iron. Iron is very common in the universe. Indeed, a famous man named Ira Bowman was a spectroscopist and astronomer, and made the connection between atomic physics and astronomy, as I'll show in a minute. So he trained in Oberlin, he got his bachelor's at Oberlin, and then went to the University of Chicago for his PhD work. And he began working in 1921 with Robert Millikan, who was one of the first Nobel Prizes in physics that the U.S. produced. The Millikan oil drop model has to do with with electrons, quantum mechanics. So he basically then was, in Robert Millikan's group, his crib maybe, in Gen Z terms, and moved out to Caltech with him. And the interesting thing about Caltech is that there's a lot of smog in LA now, but at the time, Mount Palomar was a fabulous telescope. It's the one that Edwin Hubble would later use to first show that the universe is expanding in redshift. Fabulous telescope in its day. So then I mentioned briefly Bowen fluorescence before. So first of all, what fluorescence is we use lasers at the checkout all the time. So lasers are basically a fluorescence phenomenon. It has to do with something like taking a whole bunch of atoms in a low energy state, pumping them up to a high state, and then they transition down. And when they transition, for example, a helium neon argon laser is the red light that's often used for scanning particles. So basically, it's pump it up, and then when they come down, that's called fluorescence. So a laser is a simple supermarket example of fluorescence that we use every day. It's not the same thing as astronomy. And Bowen, in fact, was trying to explain something which people call nebulium, because it was seen in nebulae, which are gas clouds in the universe. So Bowen actually realized that it was not an independent element, but it was just a form of oxygen. It was oxygen with one electron taken off of it, which we call oxygen 2, O1 is the neutral one. He also discovered later that doubly ionized oxygen and singly ionized helium can actually form a laser. So the helium pumps the oxygen up, and then the oxygen fluoresces. And in all these situations, I should say, just like helium neon lasers are always red, right? They're never green or blue. Quantum mechanics says that the energy state between two levels of an atom is defining that color. So there are particular lines of oxygen, and only of oxygen, and only of the ionized oxygen, that are the monofluorescence lines. So, and the statement is that's something that maybe I could get to a little bit more, but by some very basic physics equations, you can show that you can solve for both the density of the material that's emitting the fluorescence and also the size. basically conservation of energy and the total amount of energy that you're looking at. So basically. So my dissertation then was two approaches. I mean, again, this I think is to get you in the frame of mind of Chandra, but also to show you again the involvement of atoms. So we tried to make a star in the lab. So that means that we have to ionize helium once and ionize oxygen twice, and then we wanted the atoms to collide and for them to do fluorescence. The thing is that you need very high speed for that to happen. I think you're all familiar, some of you maybe, with the Doppler effect. So that if they're not moving, then one can't help the other. But if one is moving, as you have high speed in the clouds around black holes and things, then you may have enough to see these things. So it was a very difficult experiment in the lab, and it failed. You never saw that. On the other hand, our other line of investigation was astronomical observations at one of Berkeley's telescopes, the Lick Observatory, which is the one that he used heavily before Keck. And what did we look at? We looked at compact objects because we felt that those were the ones in which there would be enough ionization and enough speed to be able to see this phenomenon. And in particular, compact objects are cool. What are compact objects? Well, after a star exhausts most of its core hydrogen, which has been fused into helium, it has nothing supporting itself from gravity. On the Earth, things fall down. In space, things fall in. And if nothing's keeping it from falling in, then it would, collapse to a radius of about, 7, 8 miles, 12 kilometers is below that. The whole thing will just collapse to a point. That's a black hole. But there are other stages. A white dwarf is something, it's a gas of electrons. And that's something which a star could be 100 times the size of the Earth and collapse to the size of the Earth. So that's the whole, when I was growing up, they said a white dwarf is something where a teaspoon weighs a ton. And that's about right. So it's really 1 million times as concentrated because it's 100 cubes all being pushed. And neutron stars are somewhere in between. But basically, in all of these conditions, you do see a lot of X-rays. And so that makes it X-ray astronomy. And you do have this compactness. The compactness is something that comes out of relativity that says that you have a lot of mass per size. So you're squeezing it. But if you have the idea of collapsing, that they're collapsed stars, then you'll realize, it could be very dense. Right. And in fact, given what the mass that you see and the energy you see, you're basically literally turning mass into energy in these cases. They're so efficient in producing X-rays that the only way it could be produced is by relativity, which is, I think, cool. All right, let's keep the slide. This is my computer that's skipping, it's not anything here. Let me talk a little bit about a giant in X-ray astronomy, Riccardo Giacconi. So basically, I used this telescope outside San Jose, California, and I was looking at optical telescopes, like the one that Donna says, that will be something that you can look through. It's typically a refracting telescope. But X-rays don't get through the Earth's atmosphere. UV does, it causes sunburn, but X-rays don't, which is a good thing. So you have to fly a rocket, maybe you get a couple of days out of that. A balloon, you might get a month, or a satellite, and then you may get a period of years. But you have to get out of the Earth's atmosphere to see that. So in 1962, we had the dawn of X-ray astronomy. A series of Massachusetts astronomers, we knew that the sun produced X-rays, but we didn't know that any star produced X-rays. So Giacconi led a group which found that Scorpius X1, which means the brightest X-ray source in the constellation Scorpius, is a very strong X-ray source, much stronger than the sun. Again, that's because of relativity, and the Scorpius X1 is almost certainly a black hole. That was when they were working in a group called American Science and Engineering outside Boston. But by the 70s, Giacconi moved his group to what's now the Harvard Smithsonian Center for Astrophysics. And there are 6 departments there, but his group became head, the High Energy Astrophysics Division, which is where I worked. So when I say head, that's what it means. He's regarded as the first ever X-ray astrophysicist, and the late Giacconi is the first physics Nobel in X-ray astrophysics. Now, in my postdoc, I moved to head. I left Berkeley and I went to Giacconi's institution. At that point, he had moved to Space Telescope. There were no satellites up, so I worked on older data from a satellite that was launched in the 1970s. And if you're interested, I can talk more about it. But there were basically 1,000 X-ray sources that we needed to identify. And I just want you to take away from this that the way we did that was we didn't re-observe them in X-rays, but instead we overlaid optical and radio data. So I went to Australia to take radio data. I went to Chile, which is where South America is where the new Rubin telescope is, and other places. And then you see what is at the same position on the sky, and you see whether you can make an identification with those things. And the charts that I show at the end in the movie are the same thing. They're overlaying either infrared or optical or radio on top of Chandra data. So yeah, and then in '96 is when I joined the software test team, and that's Chandra. Now, science is always, and particularly now, under threat because of funding and X-ray in particular, because you have to fly. We had some more problems than most. So while Einstein was up in the late 70s, Ricardo Giacconi and Harvey Tannenbaum, who was the director of HED when I was there, had proposed a new satellite called AXAF. They proposed it in 1976. Eventually it would become Chandra and not launched until 1999. But one thing about it is that it required the space shuttle for launch. And so in 1986, pretty much the day I decided to go into X-ray astronomy, the Challenger, alas, blew up, and all the shuttles were grounded for a long time. And so therefore there were many, many delays on satellites, including scientific satellites, like AXAF. It also required specifically one shuttle, the Space Shuttle Columbia. And before that one blew up, someone said, you know, if anything ever happens to Columbia, Chandra will not be able to fly. Fortunately, it was lost before the tragic destruction of Columbia on re-entry and the end of the shuttle program. It's because it's long. It has a very long bay. The Canadians had designed something that was very long around the outside of it. So just wait. Okay, so now someone in the audience asked me before about how you focus X-rays. Well, you can't focus them in the way that you do lenses. They don't refract through lenses. You use mirrors instead. But let me put this in context. Herc and Elmer designed the Hubble Space Telescope, and in 1990, the Space Telescope, the Hubble, was launched. But as you may recall, the lenses had been poorly designed by Herc and Elmer, and so the images were very fuzzy. They made a mistake. Spherical aberration, an ideal mirror is a parabola. And a parabola, if you remember your math, focuses to one point. But if it's not exactly a parabola, if it's more like the surface of a sphere, then the image is blurry. And that's not very good for astronomy. So that was a failure, and it was another failure of the space program, which we didn't need 4 years after Challenger. But beginning in 1993, they figured out ways to fix it, replace the hardware with an instrument called CoStar. Now I mention that because Herc and Elmer was also involved in Chandra. Indeed, the mirrors for Chandra were going to be produced by Herc and Elmer in the mid-90s. Well, we already had the experience with Hubble, So Congress said, okay, if Perkin-Elmer is going to make the mirrors for another mission that flies on the shuttle, then we will impose a requirement that they pass a congressional test that these mirrors are okay. That there is no spherical aberration, and we don't, yeah. So, just a little bit of trivia. In the interim Hughes aircraft that bought Perkin-Elmer, no one wanted to be called Perkin-Elmer anymore. They were in Danbury, so they said, why don't you call us Hughes Danbury Optical Systems, or HDOS, right? Then you'll forget that Perkin-Elmer was involved in the Hubble Space Telescope. Well, the joke we had a bunch of instrumentalists going back and forth from Cambridge to Danbury, and they basically said, we will call the Perkin-Elmer until they pass the congressional test. So basically, what is Chandra then? It's a satellite, and satellites can, just like ordinary ground-based telescopes, can take images and they can do spectroscopy. They can take spectra. It was a joint project led by the High Energy Astrophysics division at Harvard, but with collaborators from MIT and Penn State. And my role was basically making sure that, like with Hubble a little bit, that the guide stars, if you're not familiar with telescopes, the sky moves, like the sun rises and sets, and the moon and stars set. So if you want to look at a fixed point, you have to guide on another one to make sure that you don't have blurry images. Otherwise, you'll get other astronomers call them trails. Stars will look like a trail in a photo because it will keep moving. So there was a guide scope on Chandra, and my project was to make sure that if it was looking at a star, that it really was a star and not a blur, and secondarily that it didn't point the detectors toward the sun because that would make the mission a short mission. It was launched in 1999, as stated. Eileen Collins became the first woman to command a space shuttle from Cape Canaveral. It was at midnight. It was very cool. It lights up the whole sky. It makes it look like Broadway. Okay, so what was on Chandra? Well, there are basically two main instruments, ACIS for imaging and the ACIS for spectroscopy, and the HRC, you can see as a camera, for imaging, for taking photos. In general, here's a little bit of physics if you're interested, because when you design a telescope, you want to know where is it sensitive. Hubble can only see in the visual range. There are infrared telescopes and so on. So this is a little bit of, it has basically two ranges, a high energy and a low energy range. And key in this low energy range, well, first of all, you may not be familiar with kilowatt electron volts. So they can be converted to nanometers. And I'll do that down here. A very important line right here is to see in the spectrum is iron. It turns out that iron is like the big garbage dump of the universe. I'm from the city, the big Staten Island of the universe. That everything goes into iron, that's because of the curve of binding energies, which I think was discussed in Oppenheimer, the movie, but should have. It's basically the lowest energy state. Let's go to the low energy state. So 6.7 kilovolts, which is the same as about 8 nanometers, is a very strong line of iron, but because quantum mechanics is unique to iron. So often that would be something that you see. Again, this is iron, which has 26 electrons, with 25 of them taken off. So there's only a single electron. It's called hydrogenic iron, because it's a single electron. Yeah, I mean, the numbers are maybe more for telescope jobs. So in the top right, in the red box, you can see, because people will say, well, what about x-rays like when I go to see my doctor? So those are typically going to be higher than what we have here. We want to look at x-rays where things are actually interacting with atoms. And I'm sure you'll agree, when someone's taking an image of your body, you don't want it to interact with your tissue, you want it to pass through. And at higher enough energies, basically, yeah, 50, 100 kilovolts, it'll go straight through, and you'll see the bone, the broken bone, and things like this. Okay, so now a little bit about Chandra, who is the namesake of the telescope. His full name was, I'm going to try, Subramanian Chandrasekhar, but his nickname was Chandra. He was an eminent Chicago astrophysicist from 1936 and was awarded the Nobel Prize in Physics in 1983, essentially for his own PhD work, which I'll talk about in a minute. But he did have some great students. You may have heard of Jeremiah Ostriker or John Osterbrock, who is one of the great spectroscopists and one of the first people really to take whole fluorescence measurements. Chandra's own PhD was interesting because he discovered the first white dwarf, or rather, he was a theoretician, so he explained that the reason that a star could collapse to the size of the Earth, remember, 100 times smaller in radius, so a million times volume, was because the gas inside it couldn't be squished any further together. Electrons don't like to be very close to each other. There's something called the Pauli principle in quantum mechanics, that you just can't squeeze things together. So it's relativity and quantum physics is what's keeping the white dwarf together. If physics doesn't turn you on as much, you can say that as far as stellar evolution, white dwarfs are basically the fate of stars perhaps less than 5 times the mass of the sun. So our own sun, for instance, will one day be a white dwarf when it runs out. It's the equivalent of, probably some people still have wood fire. It's like the ember is at the bottom of the fire that's very slowly, going like that. And I had a Berkeley, Frank Shu, a great astronomer, who said that small stars are like poor people. They spend their energy very, very slowly. They don't go out and bang. The alternative is a star that's more than 5 solar masses, maybe 10 solar masses, and those can blow themselves completely out of existence and cause a supernova and perhaps a neutron star, or they can completely collapse to a black hole. So that would be like a rich person, that they're spending their money, they're very showy, and they blow up. Both neutron stars and white dwarfs are sources of X-rays, but Chandra was the first to apply relativity like this to astrophysics. He was also a very dedicated teacher. There was a situation where the astronomy department of the University of Chicago was south of the center of the city in Hyde Park, but their observatory was up in Wisconsin to get away from, city lights, smog, etc. And it's almost 100 miles north, so it would be a 2-hour drive. Why is that interesting? Well, in the late 40s, post-war, the department, which had been teaching classes up in Wisconsin, and that's where Chandra had his office, said, we really want to teach them in Hyde Park, in the city. So that meant that potentially faculty would have to travel to teach the classes. There was no Zoom in the 1940s, so they would have to be in person. So one year, Chandra taught a class of physics. Only 2 graduate students signed up for it. So he could have canceled the class, but he decided, you know what? These are 2 committed students. I'm going to drive back and forth from, 100 miles to teach in Hyde Park. And my co-author on the book says the reason he did that is because they were very good students. So who were these people? Well, that would be Li and Yang, who won the Nobel Prize. So you can say the entire class that he taught won the Nobel Prize in 1957. These were 2 Chinese student eminent. One is still alive, actually, at 103. Yang is still alive. And what they were awarded for was not astrophysics, although Li did his dissertation on astrophysics, but was the fact that things at the elementary particle level don't look the same if you look in a mirror, which is very strange. Now, I was talking before people came in about the new Rubin telescope. Rubin, unfortunately, was the product of gender discrimination and could have won the Nobel Prize probably. She applied for a PhD at Princeton in the 40s and was told, no, you're a woman, you can't do a PhD in astronomy here. So that was really terrible. Almost as bad as that was Qin Wu, sometimes called Madame Wu or Liz Wu, who basically did the experiments to show what Li and Yang asserted in theory. But she never got it. And could have had a share of the Nobel Prize, but she was denied. Later in life, she was awarded a Wolf, which is regarded as second best to Nobel, which was awarded by Israel. But, you know, Li and Yang, it wasn't their, I mean, they definitely advocated for Mrs. Wu for, you know, for her to win a prize. But that's regarded as one of the great slaps to someone who do that work to prove basically their point. Okay, so that's enough about Chandra. The satellite itself, now we can start to look at some results. And so I picked a few of these, and then at the end we can do requests. So here's an example of Saturn, obviously. And here's Chandra.harvard.edu is the mainstay of everything that I'm going to present from now on, and as a public site. So, as I said before in my own dissertation work, we overlay, in my postdoc work rather, we often overlay X-ray data with other data, like the James Webb Space Telescope, the JWST, I guess the Rubin Telescope coming soon, and with Hubble, or with infrared. So over here, the blue is X-ray, and obviously the white is what you see with the visual telescope from the ground. So it turns out that these are fluorescence of water, particles that are part of the rings. These are rings that you can't see in the visual, but you can see them in the X-ray because of their water fluorescence. It looks kind of like a Christmas tree. Sorry. A black hole. Now I go to a black hole. So this is a black hole with jets shooting out of it. Jets often are very close to the speed of light, spewing out. And the artist's concept looks better than the X-ray. The X-ray is in the top right, and overlaid with radio image. But you know, you basically see, you can faintly see the jet kind of up here. That show up, yeah. Anyway, but that's what it probably really looks like. So it's pretty cool. The VLA is a system of telescopes out in the Arizona desert, and instead of one very large radio telescope, that's a so-called interferometer. So you have pairs, I believe it's 40 pairs. So that means there's 40 times 39 over 2 pairings that you can use. And the more pairs that you have, it does go essentially like n squared, the sharper an image you can get. I worked with VLA data for my postdoc. So a black hole is stated was a dead star. So what about a young star? Well, you've probably seen in one form or another these fingers from Hubble, because that was a fabulous image. So they're usually, I guess they usually go up like this. So this is an image in which we show them that they're running 45 degrees. It's called the Pillars of Creation. To me, it looks like something in the desert or maybe termite hills, I'm not sure. But it is M16, which you'll often see that people went out and found interesting things. So Messier, a French astronomer, found a whole bunch of things. The first one, M1, is the famous Crab Nebula, which some of you may have seen. So this is the 16th object in the Messier catalog, M16, and known to be a star-forming region. In this case, the infrared is showing you the dust clouds where stars form. Just like with collapsed black holes, you basically have what's called the Eddington limit. Oh, Eddington was Chandra's PhD advisor at Cambridge. So Eddington showed that if there's enough mass around the dust, that it can collapse and have enough mass to start fusion and then become a star. So these are stellar nurseries, they're sometimes called, baby stars. And the X-rays then are from these toddler stars. When they first start out, they can produce a lot of X-rays. So the X-rays are, I mean, this looks even more like a Christmas tree, but basically the different red lights. Just like with the Saturn photo, these are not real colors. You can't see X-ray colors, but they're just made like that. It might be such that, you know, the blue ones are higher energy and the red ones are lower energy, or temperature, or a lot of this information is on the archive. So you can say I didn't do my homework, so I don't exactly know what the color scheme is here. But it does tell you something about the classification of the stars. Now, this is a movie. First let's see, it may start. If I do this, yeah, now they're both starting. So on the left, you have, they're both supernova remnants. The left is cast A, which is, I think, more spectacular, but it may be hard to see the changes in it. This is, it's not quite a movie. It's a slideshow running through successive years in the lower right. And it has a mind of its own, so it may stop and then I'll have to restart it. But basically, you're seeing, well, let me read my slide. So first, as I said before, a supernova is a rather massive star, like a rich person blows itself out and leaves a neutron star somewhere in the center of it. It goes boom. So in cast A, what you're seeing is, I'll start the movie up in a minute, but the debris, the stuff from the exploded star is expanding, and we can see that with Chandra. In the case of the Crab Nebula, the rings, you can see that there's successive rings in it. See, this is where I don't know whether we got the room dark enough for this, but you can see these things. I think this mainly moves to the lower left, and this maybe moves to the upper right. Anyway, let me run the movie again. If we focus on one of them. Yeah. I don't know how much of that can be seen. I can see that.
I'll do it. I'll do it.
Right.
I can turn the light off for a second if you want.
There are shock waves, and you can also see the jet is changing in form. So that stopped again. So, nope, it's still running. Is that easier to see? Especially the lower left, the jet is changing a lot over the years. So this is over the lifetime of Chandra. This is something that we continue to go and look back at it. So it's like on a nature show when flowers go to not photography, but over here. Like you know, these are all on the site, so you can play this video. Play it one more time. Oops, no, now I'm in the next slide, so I'll stay here. And then there are these great composite images where you have a ton of things. At this point, I'm just showing you one thing at a time. In the center of the Milky Way, there are quite a few sources. In fact, the Einstein satellite 1E means that that was something discovered in the 70s, you know, the data set that I was working with. There are clouds, there's a ton of things in this field. Because if you remember a spiral galaxy, the reason you see the Milky Way, oh, I have a trivial thing. Does anyone know where the word galaxy comes from? Okay, so galaxy comes from the word galactos, which then, it's Greek and it means milk. So the idea of the stars being Milky Way goes way back, a milky thing. So from galactos, we get, you know, we get the lactic part of it, like lactic acid and lactose, but galactos, that's the word for galaxy. So yeah, so what did I do here? So this is the composite image over here, and it's labeled. I couldn't get the same labels on these two, but this is the Chandra image, so this would be emphasizing the more high energy ones. It's 10 different things. It's a cloud, Sag A, I think, is a black hole. Yeah, you have to go online, everything. And this is the radio image. There's a telescope in South Africa. A little trivial fact about the center of the galaxy, if people haven't talked about it, is, you know, there was sort of this bias that people thought that the sun was at the center of the galaxy. And one of the reasons they did that was because most of the telescopes were seen from Europe and north of the equator. If you go south, like to South Africa, the bulge at the center of the galaxy is very clear, and it doesn't take long to figure out that we're nowhere near the center of the galaxy. We're like 2/3 to the edge of the galaxy. But you need Chile, you need Australia and South Africa to be able to see that. That's all I had prepared. Let me just run, because I sort of annotated these references. In addition to Chandra.X-ray, Chandra.Harvard.edu, you can go here, and then you can see individual, you know, if you have your favorite star, you can look it up there, or you can look up. But I'll show you that they have an interface such that you may not have to do that. The Einstein Slew Survey is what I worked on for my postdoc. Maybe of interest. This is my thesis. And this is what the Fed came out with after the great financial crisis, when they said, if we have these trillion-dollar portfolios, we have to get a handle on the mathematical models. That created the cottage industry that I'm in now. As far as astronomy sources, Chandra is biographied here, and there's his Nobel Prize speech. Giacconi, I've got the Nobel Prize speech, a book that he himself wrote, and his obituary, written by a colleague of mine at Harvard. And Ira Bowen, the one for bone fluorescence, you can read more about it here. So now, depending on, I see we're getting close to 7, I can show you that if you don't have to do that here, but if you go to this site, you've got lots of choices. You can see that you can see that these are all the images of Chandra that have been made public for every year, starting in 1999 to the present. You can look at the different kind of astronomical types. Some we didn't talk about that much, like clusters of galaxies, or even we have microwave background listed. No, ordinary galaxies also do it. Exoplanets, planets outside the solar system, and so on. So, depending on time, I'm happy to go into these or take requests on what people might want to see, or we can end it there, or we can go right to questions.
You have a few minutes to?
Yeah, that's right.
Yeah, you can.
Want the light on a little bit?
Sure, yeah.
How about that circle galaxy? Is there a way you can figure out how?
Is it under normal galaxies? So then if you go into one of these, you'll see one of these.
It's the circle.
Is it, I don't know, yeah, usually you can see the New Galaxy Catalog is a common index. I mentioned Messier's Wiki. ARP is like probably the weirdest cataloger of galaxies, but it's sort of like finding a restaurant. There are a lot of different ways that people rank galaxies, or rating restaurants. So I don't know. Yeah, if you knew the NBC number or something like this, then you could look it up.
When you showed that image of the formation of the stars,
Right.
and
M16.
Yeah.
Yeah.
That image, is that actually an infrared image that you see coming right out of the telescope, or is that like an artist's rendition?
No, those are images. The only artist rendition was the jet, because you couldn't see the jet very well. The rest of them are all
So the infrared, you really see the whole thing?
You see the dust.
Okay.
You don't see the stars. Yeah, and infrared, by the way, in most cases you have to fly. You can see things on the ground in the optical, but there's a limit in terms of what you can see. In space, it's quantum mechanics that limits how fine you can see
But
stuff.
with the X-ray, we only see little dots.
These are images, it depends what you're looking at. I mean, if we looked at clusters of galaxies, there's probably big things. Well, I mean, the Crab Nebula you saw, those are big circles and things. So it depends. And yes, in that M16 field, you just saw dots. But there can be, merging galaxies, things like that, where the X-ray emission could be, is this an art? Oh no, this is an artist's illustration. But there are real images in here. I'm just going around. So, filaments of clusters of galaxies. So these are galaxies spread over, parsecs, millions of light years out.
Dr. Can I ask you, I'm not a scientist,
Okay.
so my question is sort of darn basic, I apologize for that. But what I'm still trying to understand is our sun. It's got the power and the force to blow itself up, but it's got the gravity to pull itself back together again.
Right.
Is that the counteracting forces that you're talking about?
Well, it's when the sun, at the moment, the sun is in a steady state, I can tell you. In other words, the sun isn't going anywhere anytime soon.
Sure.
If it were, then maybe it wouldn't be 100 degrees in the city tomorrow, but it looks like it's going to be anyway. It's because it's on the main sequence. It's a middle-aged star, and it still has lots and lots of fuel. Come back and check back in a couple billion years, and it will have exhausted its core hydrogen, and then it would collapse and probably become a white dwarf.
But my question again is like the energy is pushing out.
Right.
versus the energy is pulling it back together again.
Gravity's pulling it back.
And it's just constant, it seems like it's constantly fighting each other to stay there. From my
Yeah.
understanding, I'm not a scientist.
Right, that's right. Yeah, so I can't say that, and I can't say it's fusion, but fusion is basically, it's hot enough so that that's enough pressure to resist the force of gravity. Just like an thermonuclear bomb is a very,
What we're seeing here is, I hate to use these phrases, it's the same basic concept. It's one force pushing one way, the other force pushing the other way.
the basic forces of physics, I mean, Newtonian physics largely applies, yeah. There's also things like, bending of light because of large massive objects, relativity and quantum mechanics, but there's a lot of basic physics in here.
Thank you.
Yeah, go ahead.
So, given all the challenges and the testing and all the effort that went into the success that you see on the screen, and all the science developed from this, is there anything on your wish list that was missed as a result?
It's still operating. It was supposed to operate for 5 years.
Is there anything that you wish it could do that it can't at present?
I mean, there's an active, I'm no longer proposing for it, but people are constantly, every 6 months or a year proposing for new things for it to do, depending on sometimes on discoveries in other fields of astronomy or physics discoveries. So the answer is yes, there's a lot, but I'm not in the field anymore, but it's a very active, and the fact that it's been able to last 26 years instead of 5 is, I think, pretty cool.
Any idea of the correlation between X-ray phenomenon and gamma ray bursts?
Yeah, we didn't, I don't know whether, so for gamma, but for that, there's certainly, I worked on gamma ray data. Some of that was done at the Naval Research Lab. The Navy does also some peacetime scientific research, and some of it is very good. So gamma ray bursters were a phenomenon that we studied with the gamma ray telescope that went up. In fact, that was one of the things I thought about doing after leaving Harvard, but it didn't work out. But so there we were looking at gamma ray overlaying X-rays. The bursters have jets, and they're even more extreme. In the gamma ray, there's really nothing besides bare electrons, a plasma.
But you do see the correlation. Do you see X-ray objects at the point with gamma ray?
Yeah, sure. I mean, it doesn't say gamma ray. Maybe if we look at miscellaneous, it might have gamma ray bursters.
Right.
Or on the cosmic road trip, whatever that is. So I encourage you to surf around with it.
I have a question. The funding for Chandra, right, was, there was a lot going on last year, I remember, about Save Chandra, right? Yeah, and then basically I think NASA decided to refund the project. That's correct.
Donna mentioned that there's a Friday happy hour that I co-organized in '92, and those are basically my old Chandra friends. So anytime I'm in Cambridge, I talk to them, and often I drop in on the Zoom. But yeah, funding, particularly with this new administration, we don't know what's going on. It's NASA funding primarily. You've heard a lot more about, let's say, NSF and NIH funds being taken away from the rest of Harvard, but they're also not Harvard. They're the Harvard Smithsonian Center for Astrophysics, so the stuff goes through Smithsonian, but then Smithsonian is also under fire, so it's not a good time to be a scientist, but for the moment my friends are eating and working, and Any other questions?